In this lesson, we are going to be learning how to multiply a monomial times another monomial, as well as a monomial times a polynomial. We'll start with monomials times monomials. How do we know if something is a monomial? Well, monomial has a prefix, mono, which means one, meaning it's just got one term. Sometimes one term is as simple as a number, like the number 5. Other times we see it as a coefficient and a variable. Or what we have been working with is usually a cluster of coefficient and variables together. One important thing when identifying monomials is that you will not see any addition or subtraction between them. A monomial that is added to another monomial automatically becomes a polynomial. Let's see an example of what a monomial looks like in a multiplication problem. I know that these are two monomials because as I look within the parentheses, I see a coefficient and a variable multiplied by each other, but I see no addition or subtraction. I see the same thing within these parentheses. This is a monomial times another monomial. When we're multiplying monomials, we're using the strategies that we've been practicing in the last chapter. We're going to be multiplying the pieces that are somewhat of the like terms or that go together. For example, our two coefficients are both coefficients. We're going to be multiplying 5 times 4. The other piece we have that goes together here is x squared and x to the negative third. We're also going to multiply x squared times x to the negative third. When we're done with those calculations, we'll multiply those two pieces together. 5 times 4 is 20. X squared times x to the negative third. Our rules say that what we're going to do is add these two exponents. 2 plus negative 3 leaves us with x to the power of negative 1. I can't leave a negative exponent where it is, and we know that if an exponent is negative, he's not pleased where he is. So that means we are going to make a change. We're going to leave 20 in the numerator position and bring x to the power of 1 to the bottom. Now, to really professionally refine this, we don't typically write numbers to the power of 1. Because we all know that when something is to the power of 1, it will just equal itself. So my final professional answer will be 20 divided by x. In letter B again, I can see that I have two monomials because within the parentheses, I don't see any operation happening except for multiplication. There's no addition or subtraction. We're going to approach this the same way, multiplying each separate piece of the first monomial by the second monomial. So we'll start with those coefficients. We're going to multiply for the first piece of our answer, negative 3 times 4. Then we will take our variable of x and we will multiply x to the power of 3 times x. And last, we'll take our variables y, multiply y squared times y to the power of 5. Negative 3 times positive 4 will give us negative 12. That will be our new coefficient for our answer. The rules for multiplying monomials, as we've learned, say that if we have the same base, we add the exponents. When we have a variable that does not have an exponent, or a number that does not have an exponent, there's sort of an invisible or implied 1 there. So 3 plus 1 is 4. Our x value in our new monomial, or our x piece, will be x to the power of 4. For y's, we're going to use the same strategy where we add our exponents. We have a 2 and a 5, so our y's will be y to the power of 7. We put all of those pieces together, and our final answer is negative 12 times x to the 4th, y to the 7th. Letter C differs from the others because if you'll notice, some of the monomials in this example have a coefficient, and some, like the middle one here, has only the invisible or implied 1. There is no extra coefficient. The first monomial has an a and a b, the second has an a and a c, and the third only has a b. Well, we know our rules of multiplication say that we can only multiply pieces of this monomial that have the same base. So we're going to work step by step. We're going to start just like we did before and work with the coefficients that we have. Now technically we do have a 1 in this middle piece, but we know if we multiply anything by 1 it won't change our answer. So we're going to take the first piece of our answer, our new monomial answer. We're going to multiply 1/2 times 6. For the second piece, we will multiply any a's that we have. And as it turns out, because there are no a's in the third monomial, we will only be multiplying a to the power of 3 times a to the power of 2. We have 2 b's as well, one in the first monomial and one in the third. So that multiplication will look like b times b squared. And then we do have one last piece with our c. There are no other c's, so this will get tacked on to the end of our answer and remain as just c squared. Let's go through and answer our mini multiplication problems here. 1/2 times 6 is 3. Remember that multiplying anything times a half is the same as dividing by 2. For the second part of our multiplication, a to the third times a to the second, we'll add those exponents, and our final answer will be a to the power of 5. As for our b's, we have that implied 1 again. There's that invisible 1 that's going to make our letter b's total b to the power, whoops, I wasn't doing parentheses on any of the others, b to the power of 3, and then finally our c squared that is tacked on the end. You'll notice we've got everything in alphabetical order, and that's kind of the way that mathematicians like to do their work. We start with our coefficient, and then all of our variables with their exponents go in alphabetical order. And there is my final answer. If you could follow along with these 3 pieces, then you can multiply monomials. In these next few, we're going to be multiplying monomials times polynomials. You can recognize a polynomial. The prefix poly means many. So essentially, a polynomial has many monomials attached, and they're typically attached by addition and or subtraction. So for example, a polynomial might look like 3x squared plus 4. Technically, that's called a binomial. Bi, just like a bicycle, having 2 wheels means 2. A polynomial can have more than two pieces as well. A polynomial could be polynomial could have three pieces. There's one monomial here, plus another monomial, plus another. This is all together, if I were to put parentheses around it, a polynomial. So you'll be focusing on multiplying in a slightly different way when you have a polynomial. For each of the examples in this section, we're going to be looking at two different strategies for multiplying a monomial times a polynomial. In either strategy, you will end up with the correct answer if you do the math correctly. After the first two examples, you may decide you like one approach more than the other. Feel free to go ahead and just use the approach that makes the most sense to you. We're going to start with something that's pretty familiar to us. We've been using the distributive property all year, and we used it quite a bit when we were working with systems of equations. If you'll notice, you've got here this coefficient of 5, and it's right next to parentheses, very much like a typical distributive property situation or problem. We're going to treat this the exact same way, and we're going to multiply 5 times each of the terms of this polynomial. We're always going to make sure that we pay attention to the signs of our numbers so that we get the correct sign and operation in our final answer. To begin, let's multiply 5 times 2x squared. Because 5 is a coefficient, we can only really multiply it times the coefficient piece of our term. So our answer to this first arrow is going to be 10x squared. Next, let's multiply 5 times x. 5 times x gives us positive 5x. Remember that your positives can morph into addition signs and then back again when we're doing algebra. Last, our 5 gets multiplied by the 4 to give us 20. And our new polynomial answer is 10x squared plus 5x plus 20. There's another strategy that we can use. Even though it seems a little silly for this, it's a strategy that is really helpful when we start multiplying polynomials times other polynomials. So at this point, it could be one that you might want to get used to. We call this a lattice approach. And the lattice approach is kind of similar to the lattice multiplication you may have learned in elementary school. We set up a lattice that has enough room to place our first number being multiplied, a 5, down one side, either the column or the row, and enough boxes to accommodate all the terms in our polynomial. So we'll have 2x squared plus x plus 4. In this case, we're going to be treating this entire lattice very similar to a multiplication table. In this square, or rectangle, since I didn't make perfect squares, we're going to take the two pieces that feed into it and multiply them. You've got 5 times 2x squared to give us our product of 10x squared. Here, we'll take x times 5, positive 5x, and in the last space, 4 times 5 will give us positive 20. If you write it outside of the squares, you'll see that we got the exact same answer when we tried either strategy, 10x squared plus 5x plus 20. For example B, we'll try that distributive property approach again. Now, the number being multiplied on the outside is no longer simply a coefficient. We've got 4a, so we also have a variable to consider when we're multiplying. We're going to multiply 4a times a squared b and also times 2b squared. This might take a little more writing on my part so that I can make sure that I'm using all of my rules correctly. This first arrow says I'm going to multiply 4a times a squared b. Well, when I take a look, I have nothing to multiply my 4 by, but I do have two a's being multiplied. If I remember that I have an implied 1 next to that a, and I also recall that my rules say if I multiply two of the same base, I can add the exponents. This would turn into 4. If I go back to my variables, I notice this has an a and this has a b. Those are two different bases, so I cannot do any math that includes both of those. It looks like my a will remain the same. It also looks like my b squared will have to remain the same. Now I have to think back to the fact that my 8ab was positive so that I can properly record that there is a plus in between those two terms. My final new polynomial is 4a cubed b plus 8ab squared. All right, so if I were creating a lattice to complete this problem, I know that I have one piece of this problem that just has one term, so I only need to go down one row. But I do have two pieces of a polynomial that need to go across. So I'll make my rectangle large enough to write inside. I'll make sure I have a 1 by 2, and I have 4a as my first monomial, my first piece that I'll multiply. And I also have a squared b plus 2b squared. Now remember, we treat this like a multiplication table, so we multiply this times this, and then we fill it in this rectangle. 4a times a squared b. There's nothing to multiply my coefficient of 4 by, so that 4 is just going to stay. My a's have the same base, so I can add the exponents and get a total. My a has an implied exponent of 1, and if I add that to the 2 that this a has, I will get a to the third power. Because there is no b in this monomial, I can't multiply this times anything else, so therefore it just remains a b. Now on to the next set of multiplication. We have to multiply 4a times 2b and write the answer in this rectangle. Here I do have two coefficients that I can multiply. I can multiply 4 times 2. That's going to give me a positive 8, so I know I'm going to have a plus there. I have an a in this monomial, and I have a b here. Neither of those things can be multiplied because they do not have similar bases. So I will just rewrite the a, and then I'll rewrite the b squared. If we write our answer outside of this lattice, and put a nice rectangle around it, we can take a look at the two strategies we used and see that they have the same answer of 4a to the third b plus 8ab squared. Same over here. Our last example has a longer monomial, 2x squared y, and is being multiplied by a binomial. That just means that it has two terms instead of three or more, which are 3x and negative y. Don't forget that this negative belongs to the y and will morph into a negative sign when we're doing any kind of work. All right. Our first strategy asks us to treat this like a distributive property problem, which it kind of is. You've got one thing on the outside to multiply by two separate pieces on the inside of the parentheses. I'm going to be very careful again to record each of these separately, because sometimes if I go too quickly I might miss something. So here I've got 2x squared y times 3x. If I take a look at each of these, I notice I do have a coefficient. That coefficient, the two coefficients can be multiplied so that I end up with a 6. 2 times 3 is 6. They each also have an x squared and x. We've been talking about the fact that x has an implied 1. So I'm going to jump to adding my exponents and noting that this will be x to the third. Last, this monomial, this term has a y, but this one does not. That leaves me just to write the y by itself. The first piece of my answer will be 6x cubed y. I'm going to go back to my arrows. This is the multiplication I did in purple. Now I'm going to do this multiplication in orange. I've got to multiply 2x squared y times negative y. Okay. So I notice that even though this y doesn't appear to have a coefficient, when I've got a negative there and no other number, just like when there's a negative outside of parentheses or in front of any other variable, it's always good to write in that invisible or implied 1. That leads me to actually see that I've got a coefficient of 2 times negative 1, which gives me negative 2. Here's a case where the negative sign has now morphed into a minus. Taking care of those signs is very important to getting the correct answer. Next, I'm going to look and see that there's an x squared in this term, but no x in this one. So that will get rewritten. And then it also looks like I've got a y and a y. Each of those has an implied 1, so I've got y squared. My final answer, I'll put a rectangle around. All right, if you've chosen the lattice method as your favorite, we know that we've got to create one row for 2x squared y, and we've got to create a space for 3x and for negative y or minus y. I've got to multiply in this rectangle here 2x squared y times 3x. And as I do that, I'll notice that I have two coefficients. I have 2 times 3. So the first piece of this I can do the multiplication and get 6. Secondly, I'll move to x squared times x. Because they have a similar base, we can leave the base the same and we can add exponents. So I've got an exponent of 2 times my invisible or implied 1, which will give me x cubed. I've also got a y in this term, but not in this one. That y simply gets recorded and stuck on the end. Now, when I start multiplying here, it looks like this does not have a coefficient. But we've talked often about the fact that if there is a negative and nothing else in front of a variable, it's helpful to write in the invisible or implied 1. Because now I can see that what I've got to do is multiply 2 times negative 1 to get negative 2, which then morphs its way back to a minus for my polynomial answer. I also take a look and realize that there are no x's in this term to match this one, so my x squared will get written in, and I have two y's, each with an implied 1, so y squared. If I rewrite this answer, that's in purple, 6x cubed y minus 2x squared y squared. Put my rectangle around it. Let's take a look and make sure that those two answers indeed match. And they do. Either strategy is fine, whatever you're most comfortable with or whatever makes the most sense for the problem that you're completing.